computer. Okay, I'm going to go to multiple. We're going to share the screen now. Oops, this always pops up. Where's my PowerPoint? Okay, here we go. Okay, so guys, I hope you guys tried the problem. I mean, it's the best way to practice and get prepared for the exam. So this way, if there's any glitches, now's the time to ask. Now's the time to ask me, and at the same time, you can, Okay, so basically we had a W 200 by 27 column subject to an axial load of 720 kilonewtons, not bad. And it's supported by a concrete foundation whose 28 strength is, 20 MPa. So we start off by choosing a square base plate, and then we will optimize it. And then of course, we'll see how much steel that we can save from the optimization. And then the only thing I didn't do last time, I'm going to take a little time and talk to you how to make the sketch. Okay, so I'll spend a little bit more time on that. But the sketch to me is ultimately what people want to see. Okay, they don't care about your calculations. All they want to see is what do they need to do in order to get the results that you want from your design. Now, so W 200 by 27, of course, you go to the W shapes and you go look for the D and the B. So, and like I said, you go down and it's by size, W 200 by 27. So you get to 200 by 27 and you go to the next page. So therefore, there's your D value, 207. There's your B value, 103 right there. Okay. And once you have those two values from the geometry of your shape, then you can start. Okay. So you have 207 and 133. And now, of course, you start off by calculating the factored resistance. Okay. Now, guys, the reason why I say factored resistance, I want you to keep this in mind. Okay. Factored resistance is simply because I'm always using some kind of reduction factor, and I'm not using 30 MPa. That's what we say factored resistance. Okay, so for example, factored resistance in steel, we use a phi, you understand? So, and that's what I mean by factored resistance. People ask themselves, how can we have a factored load and a factored resistance? Because here we reduce the nominal strength of our material. On the other side, we increase the load that we want our structure to support. Okay, so here, so in other words, instead of using, I use about half the strength of the concrete, or the ultimate strength of the concrete, and I use about half of it to calculate the bearing. And of course, so now, once I have the bearing, I take my CF, okay, divided by BR, and all you have to be careful about here, of course, is that either bring this to newtons or bring this, you're gonna have to worry about the units. And of course, after that, we have, so this is a required area. Now, the thing we do is if we want to have a square plate, of course, we take the square root of that to give ourselves some kind of a size. And we end up with, and I said, guys, always use multiples of 10, okay? And size it up, okay? I mean, like, unless you have like 251, okay, then you might want to go to 250. It won't make much of a difference, okay? But if anything, size it up as opposed to sizing it down, okay? So use multiples of 10. And now, so we have 260 by 260. Of course, the first thing we need to determine is which is the side of the plate that has the biggest cantilever, because basically that's what you're doing. You're designing a little cantilever that exceeds the perimeters of your column. So basically, to calculate M, you take the value of C, which of course is the same as B in this case. You take 0.95 of D. So you're going slightly into the shape, and then you divide it by 2, and I got 37.1. And of course here, the N is the one that governs. In other words, that's the one that has the longest cantilever outside the shape, and therefore that's the one that's going to be subjected to the highest bending. Now, TP, of course, is this formula. And guys, I know I don't want to bore you, but this is simply, okay, this is simply, like taking the bending moment caused by the force here. So in other words, this calculates the bending moment. And then of course, you're making sure that the MR value based on your T value is greater than your MF value. That's all this formula is. I might show you this when we're going to be doing the exterior. You know, we're going to be doing the base plates for the exterior columns. I might go into a little bit more detail to show you how these things actually get calculated. Now, the TP is 21.6, and of course, you're going to go to the see what's available in terms of thicknesses, and therefore you come down. Okay, let me just. So you come down, and of course here you see that you have. Okay, so there is a 20 millimeter 22. So you can specify a 22 millimeter because you need 21.6, but that would be like your second preference, and ultimately as your first preference. So you put on your drawing 22, and then you tell the guy, you know, you can put down a 21. So that's up to you. You're the one that specifies what you want. Okay. And therefore we end up with your second preference is 22, your first preference is 25. And of course, now all you gotta do is check the deflection. The deflection is basically n over 5. You need at least 15.4. You're using at least 22, okay? The example I got from the book, they use this value here, and I think that that is stupid because you're actually using this. So why don't you compare it to what you're actually using and not what you're actually calculating, you understand? So you are using 22, and therefore you're okay. So this is pretty straightforward. And like I said, guys, please take your time. Don't make mistakes, because when you're going to be doing the optimization, okay, now remember the optimization, okay, is based on the area that you started to size your plate. Okay, it's not on the area of the plate itself. Okay, so this is the area. In other words, this was based on the CF over BR value. So you take that area there, and you know that the B and the C value, these are the two equations for those two variables. And therefore, you're going to say that times B times C. That's what you need. And of course, how do you optimize? Now, these were the values of B and D that we got from the table. And of course, how to optimize is that you want to make, okay? Okay, so in other words, you come up with a quadratic expression here, okay, and of course to optimize, you want to make one equal to the other. Either make n equal to m or m equal to n, makes no difference as long as you eliminate, you end up with one equation with one unknown, and therefore we end up with this. And of course, if you expand this, you know, this is, I hope you remember how to expand the polynomial. And then once you have it in this, you should put in terms of A, B, and C so that you can use the quadratic equation. And of course, for those of you that have, I know that some of you have the quadratic equation already programmed into your calculators. By all means, use it. You know, use the tools you have. Those of you that don't, well, remember, this is the equation for the quadratic equation, okay? So it's minus B, and of course, that's the A value, that's the B value, that's the C value, plus or minus, okay? And of course, here you're going to have one realistic result and one that's not going to be realistic, okay? So in other words, so when I put everything in, I end up with 54 millimeters. So that's going to be my value of N and M in order to get this size of plate here based on the equation. Now I recalculate the B, and I round it up to multiples of 10. I recalculate the C, round it up to the multiples of 10. Now, since I'm rounding up, I want to see which one gives me the longest cantilever. So therefore, I recalculate my N, because this is going to be the actual N now. This was the N that you calculated according to this formula, but it's going to be the actual N. And this will be actual N. Here, it's not much of a difference here, but you should always use the higher one to do your calculations. And in this case, this is the one that governs the value of the thickness required, although it's only 0.1. I mean, it's just to be more accurate as possible. And of course, here's the equation. Now I've got all the variables. All I got to do is, of course, put all the variables in.
Can you go back to the previous slide? I just want to check my answer. Thank you.
Sure. Are we good to go?
Okay, thank you so much.
Okay. So is everything good? Did you see where, do you have the same values?
Yeah, I have the same values. It was just that I didn't calculate the M and N. I just calculated one. of them?
I'm just saying you should, uh, Rena, you should calculate both just to make sure that you're using the right one. You understand? Because sometimes it'd be a couple of millimeters more. It's just to be a little bit more accurate. That's all. I will be expecting you to recalculate these two values and show me which one you're going to be using. Okay. So if you didn't calculate one, you would have lost a mark. Big deal. But okay, so of course I put here to, in other words, this is the square root of that. And again, okay, remember, like what I like to do is I like to put my Fy. You'll notice I like to put my Fy in 0.3 kilonewtons per millimeter square, so I can cancel this right away. Okay, this cancels right away. So, and I'll be using this pretty much for all the tension members. You'll see for the Fy value, I will always be using kilonewtons per millimeter squared. And this way, I'm assuring myself that I end up with, excuse me. So in other words, this and this cancels this. I take the square root of this, and therefore I end up with a millimeter. So I have the right units, and therefore I can go ahead and, so here we go. And now if you do the calculation correctly, I end up with 15.6. And now if I go back to where I can select the flat metal products, okay, so here you see I have my first preference is a 16, so that's all I'm going to choose is a 16. I won't even have a second preference because I already have the first preference being the closest one to my solution, and therefore I'm going to say my first preference is 16 millimeters. So we went from a 22 down to a 16 millimeter plate, which is, it starts to be, like, and then on top of that, we can check deflection. We need 11.4, we need 16, we're okay. Now, how much was saved? Of course, you take the area, like we go back here, I go back here, this is where you get all the mass per area of each plate size right here, okay? So here, for example, I have 126 for the 16, for the 22 or the 25, either 173 or 196, okay? Now, if you do have two preferences on the exam, guys, just take one. I don't care which one you take. And if you did your calculation based on your second preference versus your first preference, or if you do this first preference and you show me the difference, they're both going to be correct. Okay, I'm not going to mark them wrong. So here, the 22 millimeter plate, 11.695 kilograms, and the 60 millimeter plate, 8.5 kilograms. And of course, there's a savings of about 3.1 kilograms, which is close to 7 pounds. Well, or 3 kilograms. And so there is a savings. And of course, like I said, depending on the number of columns you're going to have in your project, you multiply that by the number of columns, and then you start seeing how much you're really saving. So this is it. Any questions so far? Because the last one's going to be the sketch. Is everybody okay with this? Now, this is what I'd like you to do for the sketch. And we'll go through this slowly so that you'll know what I'm going to be expecting of you. You always show, of course, the overall size of your plate. Okay, always. Okay. And of course, so in other words, here's the overall size of your plates. And you're always going to show that this is your column. Okay. And that your column is concentrically loaded on your plate. Because if you don't show this, all your calculations are wrong. So this, in other words, all the calculations you've done is based on the fact that you're assuming that the pressure underneath the plate is uniform. And that's only when the thing is concentric. That's an assumption, okay? So that's number two. So in other words, you do not specify the column because the column gets specified in a column schedule, okay? And therefore, so you don't specify the column, you just show that the column is concentrically placed on the plate. And if you're going to have holes here to put your anchor rods or your anchor bolts, and you can have anchor rods or you can have anchor bolts, well, whatever holes you have here, they should be dimensioned with respect to, and in other words, the edge distance, we're going to talk about bolts pretty soon. 35 is a very common edge distance, okay? And so on. And here I show 4 bolts, and this is where I'm telling you, because of that one worker that got killed because the column collapsed on him while he was climbing up the column while he was erecting the steel. Now the standard requires that a minimum of 4 bolts per column, and this is not because you need it for quote unquote your structure. It's more for during erection to minimize the risk that somebody else is going to get killed. Now, don't worry about this. This is a welding symbol. We will be talking about this in a couple of weeks. Okay, so this is just a welding symbol. You'll learn about these. Okay, so if you don't put the welding symbol, I won't penalize you, but I do expect you to put holes. I do expect you to realize that you need to anchor this to your foundations. If you don't put the welding symbol, well, you know, and then of course you should specify what is the thickness of, okay. And if you guys ever want to abbreviate on your drawing plate, you can put P. This is how you abbreviate, and you put an L across it, and then you put 16, okay. And of course that's another way of you know, a shortcut of saying plate, okay. So the plate thickness is 16 millimeters and so on, okay. So that's what I'm going to expect you to do as your final sketch. And like I said, and this here, we'll learn about the welding and the symbols and what they mean. And this has like a very, very distinct, it means something very, very particular. This also means something very particular, and so on and so on. Any questions on the sketch? We're all good?
Yeah.
Okay. Like I said, don't worry about, like I said,
So
okay.
we don't show the
Sorry?
we don't show the n, we don't show the n value, only the m.
You don't show any value. All you show is your geometry, where your column is located, and where the holes for your anchor bolts are located. You don't show any M or any N. Those are your calculations. You understand? It's just like in reinforced concrete.
Okay.
You don't show the D, you show the H, you show the cover. You understand? These are dimensions that are totally irrelevant for the guy that wants to build your structure. Okay, you don't see any. Where do you see any N here?
No, I thought this 35.
The 35
I didn't
is called the edge distance from the edge of the plate to the center of the hole. So that you want to specify, you understand? Okay. And okay, and of course, okay. So that's it. That's it for the problem. And of course, we're going to close this. I'm going to close this. And I'm going to go to, now we're going to go to, today we'll talk about tension members. Now, of course, what are tension members? Okay, guys, look. So a tension member, very quickly, okay. Structural elements that are subjected to direct axial loads, which tend to elongate the member, okay. So in other words, if the fibers inside your member wants to stretch, then it's tension. When the fibers want to push together, then it's compression. And like I said, in real life, there are only two forces. It's either a push or a pull. So push is compression, a pull is tension, okay? And that's what we have. So now, and of course, when it comes to structural steel or steel in general, okay, steel loves tension. I mean, if steel is going to be subjected to any particular type of force, a push or a pull, it would rather be pulled than pushed together, okay? And that's why whenever we're doing anything out of steel, the more it can stay in tension, the more you're taking advantage of how the maximum resistance of the material, okay? And that's the thing about steel. Now, what is the design requirement? Just like any other design requirement, the factored resistance, TR, is greater than the effects of the factored force in this case, the TF, okay? So now, that's the design objective. And so TR, the factored tensile resistance of a member or component. And we say component, in other words, it can be, you know, a component. It could be a base plate. It can be whatever. It can be a gusset plate. It can be a plate that you're using to connect. Okay, the tensile force in the member component under factored loads, okay? And that means that when you're calculating the TF value in your member, you're calculating, you've already factored your loads, and therefore you're getting the TF value. Now, TR is the least of. So depending on the situation, there are three ways of calculating TR. So don't panic. We'll go through them, and we're going to be repeating this again next week. Not next week, like on April 1st, because next week we're having the test. So TR, the most basic one, is equal to phi AGFY. Okay, and like I said, why do we call this a factored tensile resistance? Is because we are multiplying the Fy value by this reduction factor. And of course, in this case, 0.9. And that's what we call it, a factored resistance. So, oops, clear the drawing. So we know that phi for structural steel is 0.9. And that's because, you know, when the mills produce the members or the components that we want to use, there's a very good quality control on the production of the steel and also on the actual rolling of the members and all that. So therefore, that raises our level of confidence that the material is going to have that resistance. Okay. And of course, AG is a gross cross-sectional area. Okay. And Fy is the specified minimum yield strength. And so far we've been using 350, but when it comes to plates, you'll see I like to use 300, and we're going to be using 300 until they start making the plates with 350, but we're going to be using 300. So that's the first equation, okay? So now here's the second equation. TR is equal to phi U, okay, times UT times AN FU plus 0.6 AGV Fy plus Fu divided by 2. Okay. Now don't panic. It looks more complicated or serious than it actually is. And if you follow me today, you'll be able to relate to this equation completely. Okay. Now 0.85. Okay. Phi U, instead of being 0.9, you drop down to 0.75. Okay. Now, what's this? UT is an efficiency factor. And what we're going to do is we're going to look at them very quickly, but we're going to come back to this. Okay. So here are the, oops. Okay. Sorry about that. So here are, UT is an efficiency factor, and UT is 1.0 used for symmetric block or failure patterns. Okay. And concentric loading, and is taken from the following specific applications. Now we're going to come back to this. Okay, so this is where you have your UT. Now, when we're going to be connecting angles, the UT is going to go down to 0.6. If we're connecting flanges, 1.0. And basically, unless we're connect, and then of course for cooped beams, and what's a cooped beam? Is that a beam whereby here's a top flange, you have cut out the bottom flange here, and when we get into double angle connection, you understand, so that's what we call a coop beam, so that you can slide it between your two double angles. Okay, that's what we call a coop beam. And if it has one line of bolt, then you take 0.9. If it has two lines of bolt, then you take 0.3. Okay, so these are efficiency factors, and in most cases we'll be using 1.0. Only when we're going to get into angles, we're going to go down to 0.6. Okay, and that's if they're connected on one leg only. So in other words, when I have an angle, okay, when I have an angle and I have connections only on one leg, then I go down to this. If I have connections on both legs, well, I'm back up to 1.0. Okay, so that's what they mean by one leg, two legs. So this is one leg here, and then you can have connections on both legs. So that's the, okay, so let me go, okay. So that's the utility. Okay, AN is now, we'll talk about this today. Okay, AN is the net area. In other words, it's the area where you might have a perforation, a hole. Okay, so AN is the net area in tension. FU now is different from FY. FU is the minimum tensile strength. So this is not the yield strength. In other words, this is the actual strength of the steel. So in other words, if you remember those diagrams where you saw the stress strain of the steel, you saw that you had this kind of linear relationship, and then this was your Fy value, and then all of a sudden it deformed, and then it went up again, and this becomes your Fu value. In other words, this is a tensile strength of the steel. Okay, And then after that, of course, it's going to break. So this is the FU value. Now, the FU value is very simple. Of course, it's higher than the FY value. And of course, so in this case here, you'll be given those values, but they're basically for whether it's 300 or 350, the FU value is taken to be 450, just to let you know. Okay, so that's the, and of course, AG is the gross area in shear. Okay, so this is where you have to look at. Is the material being broken either in tension or in shear? And that's what you have to analyze. Okay, so this is the gross area in shear. Okay, now this is the last one. Okay, TR is equal to phi U ANE FU. Okay, where ANE is affecting that area due to shear lag. Now, don't worry about this. We'll be covering this in about 2 weeks, shear lag. Okay, now we'll explain to you what this means. Today, all we're going to be worrying about is the first two, and in a couple of weeks, we'll be worrying about this third one. Okay, so don't worry about this one. But we will be going through all three equations, and especially when we're going to be doing like connections for double angles and stuff, we'll be looking at all three possibilities. So these are the three equations. Okay, now what's a pin connection? Okay, a pin connection, I got an example here, I believe. Yeah, okay. I want you to see here, you have one big pin going across this connection. Well, that's a real pin connection. So here you see the pin here. These are real pin connections. Have you guys ever gone to the Peel Metro Station? Who's been at the Peel Metro Station?
Yes,
Yeah, me.
Have you ever seen the columns that are along the platform on the Peel Metro stations?
never paid attention.
Next time you go, guys, you're going to see they have these beautiful columns, concrete columns, okay? And at the bottom, they got a steel plate, and you're going to see a perfect pin connection right there, okay? Sitting on a base plate. Next time you go to Peel, you look at the top, at the bottom, you're going to see they analyzed it as being pin connected. They actually created physically a pin connection. Okay, so if ever you go back to Peel, look at the columns that are along the platform and look at the bottom. I'm sure there might be at the top also, but just look at the bottom and you'll see this type of connection. In other words, you'll see a pin, literally, going through and holding this whole thing together. Now, if you're going to be designing that kind of a connection, well, this one has its own equation. TR is now 0.75 phi A, okay, AN FY, and AN would be the net area, and we'll talk about net areas. So this is a real nice pin connection. So these are nice, okay? Now, of course, phi is the same value. AN is the net area. Okay, so in other words, if I would be looking at this here, okay, I would be looking at the area right across there. In other words, whatever hole, that would be the net area. And of course, Fy is the minimum yield strength. Okay, so for these connections, you still use you don't use the ultimate strength, you use the actual yield strength of the steel, and that's the big difference. Whereas the other ones, when you're going through a hole, you're going to be using the ultimate tensile strength instead of the yield strength to calculate the resistance. Okay, so that's just for your general information. If ever you get involved, just remember there's a very unique equation for this one, and these values you're going to know like the back of your hand once we're finished with connections. Now, here, okay, we're going to talk about gross and net areas. Okay, so you guys can get an idea of what we're talking about, gross and net areas. Okay, right now I'm drawing here 1, 1. What I'm trying to say here, this is where I'm going to be assuming I'm taking a cross section here, or a section here at 1, 1. Okay, and of course here at 1, 1, okay, this is W and this is T and so on. Okay, so right here, if I look at this diagram at 1, 1, okay, AG is considered the gross cross-sectional area, and what would that be equal to? And of course, it would be equal to T times W. Is everybody clear on that?
Yes, sir.
Okay. So whenever we're talking about gross cross-sectional area, okay, of course, we're talking about where there's no materials removed in the member. Okay. So whether it's a plate, whether it's an angle, whether it's a wide flange, AG is AG. Okay. Now, So in this case here, if I want to calculate the tensile resistance, right at this point, in other words, if I want to calculate the tensile resistance anywhere in here, okay, anywhere in here, or anywhere in here, okay, that's all the same, okay, the TR value would be equal to phi AG FY. So once I know my phi value, and of course for plates we'll be taking 300 MPa for phi, I know my AG value, I can calculate what will be the tensile resistance that this cross section will be able to provide for me. Okay, so that's that, and that's the very first equation we did on the previous slide. Now, this is also where, for example, what happens here? Why do I have a different cross section here?
There's a hole.
There's a hole. So I'm removing material, right? So I don't have a gross cross-sectional area anymore. In other words, if I look at it from this point of view, if I look at it from this side, I have this here, right? And of course, what's going to happen is, I'm just trying to find, okay. And of course, what's going to happen is that right here, and of course, I'm looking at it from this side here, okay? Right here, all this material is going to be removed. So I don't have, I no longer have an AG, I have an AN. Okay, I have a net area right there. Okay, so therefore I cannot use the first equation anymore. I got to use either the second or the third equation. Okay, so that's AN, and of course AN is WNT, where WN is W minus the diameters of the hole. Okay, is that easy enough? Does that make sense?
Mm-hmm.
Okay, so in other words, if I start with the overall width, I take off the width of the hole, I end up with a WN, because the T is constant, whether it's for the hole or for the plate. Okay, now let's talk. I'm not sure if okay, and then D, we always represent the hole in terms of diameters. Okay, we don't talk about holes, in other words, diameters. So for example, and of course, when we're talking about diameters, we're talking about diameters of bolts that we might want to use to make our connections. And therefore, when we get into connections, you'll get to know a little bit more about bolts, but there are specific size of bolts. Okay, so for now, just bear with me. Okay, now whenever, for example, whenever I'm going to use let's talk in metric. Okay, so let's say I decide to use a 20 millimeter bolt. Okay, so in other words, here what happens is I would say, on my drawing, I would say 2 20 millimeter bolts. That's what I would say on my drawing. Now, I want you to use 2 20 millimeter bolts. That's what I need to be able to get my resistance, okay, hypothetically. Now, so I don't specify the diameter on my drawing. I just specify the diameter of the bolt I'm going to be using to make my connection, okay? And of course, the guy that's going to be fabricating these two plates to be able to be bolted together, he's going to make the hole to accommodate a 20 millimeter bolt. Now, when you're doing your calculations, okay, the holes are 2 millimeters bigger than the diameter of the bolt. So if I'm going to use a 20 millimeter bolt, I have to assume that the bolt hole is going to be at least 22. So I have to add 2 more to my bolt diameter. That's what you do for your calculation. That's going to give you the actual bolt, the hole size, okay? Now, so if it's drilled, okay, then the value of D, okay, the value of D is the diameter of the bolt plus 2 millimeters. Everybody follows? Okay, so the guy's going to take a mesh that's going to be 22 millimeters in diameter, and he's going to make the holes with that mesh, okay? Now, guys, believe it or not, when you want to make holes in steel, they're not just drilled, okay? They can actually be punched by a punching machine because it's faster, you know, bang, bang, you know, it just gets punched through the material. Now, if punched, then you take the diameter and you add 4 millimeters. Now, why do you add 4? Well, when you punch through steel, there's deformations. It's not as clean and as precise as when you're drilling. And to account for those deformations and to account for the, you know, like the area that got, you know, affected by the punching, okay? It says Punched holes are common fabrication procedures, and 2 diameters larger than the hole diameter and is allowed for distortion. So because the punching does distort the hole, so when you do your calculations, okay, if you want to be conservative, if I'm going to be using a 20 millimeter bolt, and I don't know if the fabricator is going to be using a drill or a punch, then I will automatically assume that he might be punching it. Therefore, to do my calculation, I will automatically add 4 millimeters to the diameter of the hole. That's the conservative way of doing it. Okay. Is everybody clear on that? Because this is going to be coming up over and over and over on everything that we're doing. Okay. So I just want you to keep in mind, we specify the diameter of our bolt. And then as far as the hole itself, if you know it's going to be drilled, or if you specify drill on your drawing, then you can allow only an extra 2 millimeters. If you don't specify anything, you want to be conservative, then you should, in your calculation, you should allow an extra 4 millimeters for that hole size. Okay. And we're going to be doing this in the example. Now, okay. Sorry. Okay, so here we go. Now, in this case here, because we are going through a bolt, right? AN is equal to ANE in this case, because there's no shear lag, and I don't want you to, you know, we'll talk about shear lag in a couple of weeks. So therefore, I would use the third equation to calculate the TR value, okay? So here I get, and that's what I would use to calculate TR, but for only this section. So I would calculate it here, and I would calculate it here. And of course, the smaller of the two would be governing my design. So if this value TR here is smaller than that one, that means it's most likely going to break here before it breaks there, okay? And so on. Now, what else is going to happen? Okay, so in other words, when these two things want to get pulled together, it's very possible it's going to break here, or it's going to break here. Where else can it break?
Are we talking about the bolt? For example, could the bolt be breaking?
I'm talking about the plate itself. The bolts, I'm just talking about the plates. Where within the plate can you see another section that can break off?
From the edge of the plate to the hole.
Where? I'm sharing my screen. Feel free to mock up anything you want on the screen. I believe I'm sharing my screen, so mock up anything you want. Where do you see it? Can it break here?
No.
No.
Yes, but unlikely.
No, because it's being held there and there. Okay, so it can't break there. So it cannot break there. Can you see it that it can break here?
Oh, yeah.
Ah, you see? In
didn't
other
think
words, it
about
can go
that.
through one hole, you know, shear its way across to the other hole, and then break against the other hole. Everybody sees that? Okay, so that's another possibility. So, okay. So so here's one possible failure plane, another possible failure plane. Oh, and here's another possible failure plane. Now here what happens, right, is that, okay, now here we're gonna talk about two new variables, okay? The gauge and the pitch, okay? So the pitch is a distance that is parallel to where the force is applied, and the gauge is a distance between the holes that is perpendicular. So that's how you can remember it, okay? So this is the pitch, that's the gauge, okay? Now, to calculate the net area in here, this is the equation, okay? So for 3-3, to calculate the A ant in here, you take WT, okay? So in other words, you take this, it's as if you're taking these two together, okay? And then you're adding a little bit more, just like Pythagoras theorem, you're adding a little bit more because you're going diagonally here. Does everybody see that? So instead of just having, for example, here, for example, if I would have one hole over the other, well, then I would just calculate AN. But here, because the holes are staggered, because of this little bit longer, this formula accounts for the fact that we have a little bit more material in here for this failure plane. And that's what this formula does. So therefore, to calculate this little extra area in here, you don't do it mathematically. You just use this formula here. So you take S squared times T divided by 4 times G. And G, of course, is the dimension transverse, okay, to the spacing. And S is longitudinal to the spacing. And longitudinal, always look at how the force is being applied, okay? So your G and your S, okay? So that's the formula, okay? And of course, Wn here would be 2 holes times T. And then after that, you would add this to get your total AN. Okay, now, and we're going to apply this to an example. I'm just trying to make it. Now, how else can this thing fill? Any suggestions?
Like the bolts can shear.
No, we don't talk about the bolts because the bolts we've calculated we needed 2. Okay, and the bolts are, yeah, I'm gonna show you how to calculate the number of bolts because it's gonna shear. I agree, but I'm talking about the plates now. Don't worry about the bolts. I think next week, not next week, but right after the exams, we'll get into bolted connections and we'll worry about that then. I'm just talking about the plates now. How else can the plate fail?
Like from the place of the second bolt.
Okay, so can you draw on my screen? I think I allowed everybody to participate. Can you draw?
Like same as the, like where's number 2?
Okay.
So it's gonna be like number 4 where the second bolt is. No?
Like from like, can you draw? Can you draw it on the screen?
I'm trying. Like over here. No? Or this part actually, this part.
Well, like, okay, Nermin, if it breaks here, okay, it's still connected here. But what you drew here, this is valid for the plate underneath, and that would be equivalent to number 2.
Okay, between the 2 plates, like horizontally between the 2 plates, like the 2 bolts itself.
In other words, here in the middle,
No, like horizontally.
draw it. Feel free to draw. I mean, this way, we're not playing guessing games. Draw on the screen.
And draw. Like these 2 bolts can.
Yeah. The bolts can shear off. That's going to be part of your connection, but we're not talking about the bolts at all. We're just talking about the plates now. Let's not worry about the bolts. The bolts,
how do we
we've
draw
calculated,
this?
we have ample resistance that they won't shear off. Now we're worried about the plates.
Sir, how do we draw on the screen?
Sorry?
Or does someone know?
I'm sorry. I can't hear you very loud. Can you talk? Hold on a second.
Oh, how about now?
Yeah, I can hear you a little bit better. I could put up my volume maybe. Go ahead.
How do I draw on the screen? How do I?
I think I let the participants, you can, Nermin, how did you draw on the screen?
You go from view options, David, and then there's like a drop down and you'll see annotate.
Yeah.
Go to the top of the screen, you will see view options and then annotate.
Oh, okay.
Annotate. That's it.
Would it be possible that it breaks like this? Oh, let me actually
Just draw it. Just draw it.
Yeah, like between like that and then maybe up.
Perfect. Exactly. That's an option, right? It's possible that it can go shear right through here and then breaks through here and break through there. Exactly. So that's going to be, okay. So that's really good. Okay. So I like that. And okay. So don't forget. So this is the equation we'll be using here for this particular failure plane. And then of course, number 4, just like David drew it. You understand? Okay. So that's another possible failure plane. Okay. And we will talk about this. Okay. Now, of course, we still have this here to compensate for AN, but then since here, now this is something you guys are gonna have to look at, okay? Right here, and in here, okay? The steel is in tension. Does everybody see that? That the steel is in tension across that failure plane?
Yep.
This is, you have to visualize this, guys. So, and for number 3, I'm talking about number 3. Here, the steel is in tension, right? For number 1, the steel is in tension. For number 2, the steel, everything was in tension up to now, okay? Now, so what you're gonna have to remember, okay, just for this little section here, it's no longer the tensile resistance that's resisting the steel, it's in shear. Everybody sees that? So that just for this little section here, it's in shear, and that's what all this is about. This is to calculate the value of that little bit in your possible failure plane. When the failure is in the direction of the force, the steel is acting in shear. And therefore, the shear resistance of steel is weaker than the tensile resistance. And this is how you calculate the shear resistance of the steel. But then that would be only for this little part here. So all of this here up to here would be calculated by this. Then this part here would be calculated by that. And that's what this equation does. Like if there's any failure plane if there's any section in your failure plane that's in shear, well, then you have this component here that you use to evaluate that little section that's in shear. Okay, guys, this is something you guys are going to have to just review. And once you get that aha moment, then it's going to stay with you for the rest of your life. But if you don't see this, you'll have difficulties doing these connections. Okay. And if you don't see this, then you're doing it very mechanically, and that's not good either. I'm sorry to say. So this, because of this little shear failure here under 4.4, okay, this is the part that we use to calculate, okay? Now, now the last one, I didn't want to sort of like, I'm just going to go, okay, so the last one is that it's very possible that it can actually fail this way, okay? So therefore you have a 5.5. So whenever you're looking, and of course you have a 6.6 also, okay? So in other words, it can shear through the bolts. So in other words, this would be 6.6. And we will talk about 6.6 when we talk about bolts. But right now I just want to talk about plates, okay? So whenever you're looking at a connection, okay, you have to look at all the possible failure mechanisms and analyze the resistance of each possible one. And you know, sometimes it's very tedious, sometimes very straightforward. It all depends on how the bolts are arranged, how the holes are arranged, and how the force is being applied. Okay. So this gives you a very good idea of like, you know, like what you have to visualize when you're actually analyzing a connection. You know, does it fail here? 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 Or does it fail here? Well, these are all things you have to evaluate the TR value for. And of course, the smallest TR is where it's going to tell you most likely it's going to fail. Okay. Now, let's put all of this together in a very simple example. Okay, so here I have that. And of course, because I have here I have two shear planes. Okay, I have one here and I have one here. Well, the resistance of this and the resistance of this will be calculated by this part of the formula, this here. Okay, is that clear? So whenever one of the sections of your failure plane is parallel to the force, well, that's a shear failure. Then this is the size of the equation that evaluates that little section. And whenever the force is perpendicular to the possible shear section, then it's in tension, and therefore this is the size of the equation that you use to evaluate the resistance of that part of your failure. Any questions before I move on? Okay, I'm going to have an example. Maybe the example is going to help you. Okay. So now what we're going to do is we're going to do this again, and of course we're going to do it with numerical numbers. And okay, so here you go. You have here 300 kilonewtons tensile force, okay, on each side of this plate. And of course it has to be equal, otherwise it would move. We need to have equilibrium. And of course, we have a width here of 140 millimeters, okay? And this, guys, this width is basically decided by your edge distances, by your spacing between the bolts and all that. That's how you decide these things. And we'll get more and more into that, you know, next week and the week after that. Now here I'm saying determine the plate thickness using two M49. These are very high strength bolts, okay? I don't know why I put M49 because these are very high strength bolts. And M22, whenever you see this, okay, this represents the M means it's a metric size bolt. Now, I did this because you guys are metric, but guys, bolts are all being done in imperial still. And the most common one is 3/4 of an inch would be 19 millimeters. When we're going to be doing our connection designs for our project and everything else, we'll always be using 19 millimeters. But for now, so this represents the actual. So when you put M20, well, that means it's a 20 millimeter bolt. You have M16 and so on. Okay, and then when we get into bolts, you see the different sizes in metric as well as imperial. And like I said, the bolts are still being produced in imperial. Okay, so this tells us what our bolt size is, and this tells us the strength of our bolt. There's A325. These are high strength bolt. This is still considered high strength bolt, and A490. Okay, so these are two high strength bolts, and the most common one is the A325. And when you see an M, because that's for the metric ones, and when you see an M, that's for the metric ones. Okay, so, but when we get into bolts, we'll go over this again. Now, first thing I do is I look at my failure planes. Oh, I got a possible failure plane here. Good. So now, because there's no holes, I know in this case here that my AG is equal to W times T, because I have no holes. And of course, I know that my TR value is phi AG FY. And therefore, I do the calculation, and I know that my T has to be greater than or equal to. And I do the calculation, very simple. Okay, so I try to calculate. So right here, in order for this not to break here, I need a thickness right now, right here, just there, I need a thickness of 7.94 millimeters. That's what this is telling me, because there's no holes or anything. So right here, I need a thickness of 7.9. Okay, minimum. Okay, so now, of course, I would use an 8 millimeter plate and so on. Okay, so I've checked what I need here in terms of minimum thickness, and therefore I've determined 9.4. Now, I'm going to go to the second possible failure right here. So I go to the second one, okay, which is right across here. Now here, because I have a hole, I no longer use AG, I use AN, okay? So therefore, AN is WNT, and WN is the W here minus the diameter of the holes. So what I'm going to do is the diameter of the holes plus 4 millimeters. Like I said, I don't know if this is going to be punched. I don't know if this is going to be drilled. So to be on the conservative side, assuming that they might be punching the holes, I automatically add 4 millimeters. If I knew they were going to be drilling it, then I could bring this down to 2, because that's the minimum. You always need an extra 2 millimeters for tolerances so that they can actually, erect your column or your structure. So here, so D is my diameter of the bolts, but the bolt hole I will use to be 26 millimeters. Is that clear to everybody? Is it good? We understand that? Because guys, I'm going to be doing this over and over again in the following weeks. So here we go. We've got this. Now, so I take my W here of 140, because I only have one hole, I only have to subtract one hole, and therefore I end up with 114. That's what I have left. And I hope everybody sees that. In other words, if I take a cross section here, right across here, here is my plate, here is my hole, right? And therefore what we're saying is that the amount of steel that's left here, the sum of these two is 114 millimeters. Make sense, guys?
Yes, yes.
Okay. Now, so therefore, since I'm going to, now here, I'll talk about A and E. I don't have any shear lag. Anyways, we won't get into that. So I'm going to use this formula here. Remember that the phi U value here is 0.75. It's not 0.9, 0.75. A and E, of course, is what you just, is WNT. This is your A and E value. And your FU for 300 millimeter steel, the FU is, of course, 450, okay? And therefore, okay, so I like I said, I'm going to be putting everything in 0.45 kilonewtons per square millimeters, okay? And therefore now, so that means that right here, in order for this plate not to fail, I need a thickness of 7.8 millimeters. How much was the other one? Do you remember?
7.4.
7.6. So that means this will so far governs over this one. So it's more likely able to fail here than to fail here. Okay. So that's what it's telling me. Now, the next thing I'm going to do is now go look at the other one. So I'm going to go look at the next failure plane. So here's my failure plane, right? Now we have a gauge of 80, we have a pitch of 60, okay? And then because I have this diagonal here, I'm going to take advantage of the S squared T over 4G to take advantage of that little bit more area that I get in there. So therefore, AN is WT S squared T over 4G. Now, remember, the WN value here, okay? Remember the WN value here, I'm going through 2 holes. That's what this represents. 1, 2. I'm going through 2 holes, and each hole I'm assuming to have a width of 26 millimeters. So that's how I get my WN in this case, okay? And here, of course, S is the pitch, G is the gauge, therefore it's S squared. Now T I don't know, and of course T I don't know here, and of course 4G. So therefore now this ends up being 9.33 T, and that's just, you know, to calculate this area here. And of course now I go and I put everything into the equation, and remember, use FU, okay? And I end up with 8.95, okay? So far it seems that if this thing is going to fail, it's most likely going to fail this way so far, okay? Because this is the biggest thickness. Everything else was before, okay, so far, but I'm not sure yet. Now, like I said, if we go back to the next one, now we have this. We're going to be going 4, 4. We start here, we go this way, and then we go this way. Now, remember, all this part here is in tension, and this part here is in shear. Okay, so this is shear. So therefore, this is your AGV here. So now, WN, okay, look what I'm doing for WN. I'm taking 140. Where's my, okay. I start with my overall width here, 140. Now, what does this represent, guys? 1.5.
I mean, normally a number of holes, but how do we have 1.5 holes?
Because I'm going through this hole completely here, that's 1, and I'm only going through half of this one. You see, in other words, I'm trying to calculate this width here. That's all in tension, right? Everybody follows? So here I'm going through.
Over there.
Sorry?
I did not expect that to happen.
Yeah, this is what I thought you have to set boundaries for them. So like I said, no bags, no, I didn't want him to go to the corridor yet, because I wanted him to just know this is okay for him. And beyond that, he always hesitated. Yeah. Even if we were in the kitchen or not, he always hesitated, he's like, where are they? He looks, never tried to come. But since you let him in, he knows he can go now. So now he's not always trying to go there.
He doesn't even try to go downstairs because he doesn't know how to go downstairs.
Yeah, I think he says there.
Are you guys having a group discussion?
No, sir. Someone's mic's unmuted.
Yeah, he wasn't muted.
Sorry?
He wasn't muted, but it's okay now.
Okay, I was wondering what was happening because it sounded like you guys were having a discussion. I'd like to participate. So now, does everybody understand why I use 1.5 here now? Because like I said, this part here is in tension and this part here is in shear. So therefore I want to be able to calculate the net width in here. I have a full hole in that width and I only have half a hole here. So therefore I take 1.5. Is that clear now?
Yeah, I think I get it.
You think you get it. You have to, in other words, like if I were to draw a cross section, let me draw a cross section just here, like here. Everybody understands? Here. So what I'm going to do is I'm trying to draw. So here I only have half a hole, and here I have a full hole. And what I'm trying to do is I'm trying to calculate what is the net width that I have in here. So in other words, I have half a hole here and I have a whole hole here. Therefore, I take whatever width my hole is, and I take 1.5, and this automatically subtracts this from this. In other words, I start off with a width of 140, right? Minus 1.5 the size of the hole, which is 26. In other words, this is one whole hole, and this is only half of one. And then I subtract the 30 on the other side. And that's going to give me the net area that I have from there to there. And like I said, so therefore, when I do this calculation, the net area, in other words, this amount of steel here and this amount of steel here, I should change colors. Okay, let me just put here. Okay, so this amount of steel here and this amount of steel that I have left in here, these two, X plus Y here. Okay, so X plus Y would be equal to 71 millimeters. Who doesn't agree?
I'm kind of lost. But
You're kind of lost?
yeah.
Okay, so like I said, here you're looking at, first of all, let's go plane 4-4. Okay, 4-4, right? Let's clear the whole drawing. So let's first of all, you follow 1-1. That was easy to follow? Yes, no.
Yes.
1-1 was
No,
easy to,
yes.
huh? This one was easy to
And
follow.
2 and 3. Yeah.
2 and 3 were easy to follow, right? In other words, all of this so far, this was intention, this was intention, even this one was all intention. You understand? So far, everything was intention. Now, we're looking at 4-4. So in other words, we're looking at 4-4. So right now, it's possible that it goes to there, it fills through there, and then all of a sudden I'm going to change color because it's going to be shear and it fills through there. Okay, so this part here, from there to there, of the plate is in tension. Okay, and this part here is in shear. Okay, so
Yes.
I need to calculate the net area from here to here. Okay, so if I look at this plate here like this, okay, if I look at this plate here like this, okay, I'm going to draw a cross section going across here like this, okay, and if I look at this, I'm going to, like, what you have to see, I'm going to try to draw it as realistic as possible. Okay, so here is one hole. This hole is this hole. Okay, you follow?
Yeah.
And this hole, I'm going to do it dotted because it's behind. You follow? Okay.
Yes.
This here is 26 millimeters. Now, if I look at here, okay, this only goes through half the hole. You see that?
Yeah.
So therefore, it stops right there. So how much do I have here? What's half of 26?
13.
13. Now, what's the distance from there to there? Well, if I have 30 on this side, and I have here 140, what's the distance I have here?
110.
And according to my math, 110, right? You agree?
Yeah.
So Now, what I want to do is, how much steel do I have in here? So I have all the steel here like this, right? Okay, I'm sorry. Let me just erase that. Ooh, screwed up. I'm sorry. I can't undo that. Undo. Yeah, okay, I can. Phew, thank God. Okay, erase. Okay.
So I have the steel minus the first diameter of the bolt.
Well, look, what
Plus
you're gonna have, of course, what you're gonna have is, okay, so you want to calculate the area that's here. This part, you understand? You want to be able to calculate, this is the amount of area you have in this failure plane. In other words, this is the amount of area you have in this failure plane right here. Okay, so what you want to do now, so you want to take your 110, you want to subtract your 26, and you want to subtract your 13. And that should leave you with 71 millimeters. And that's what I got here. Okay, so what you do is you start off with the overall width, subtract 1.5 bolt holes times the width of your bolt hole minus the other edge distance here, or okay, and I end up with 71.
Okay.
Okay, now, how are we doing time-wise? Mind you, we're doing okay. So now that I've got that, now here is my AGV. AGV simply goes, this is the amount of, this is my AGV here. Okay, in other words, it's this length here, that's the amount of steel that has to shear off. Okay, and therefore AGV would be 30 times T. So, okay, so that was to calculate this, the first one up here, the A and E in here in terms of T. I just want you to be able to see where I got the 71. Of course, this is just a formula. As long as you know which one is S, which one is G, you can't go wrong. And of course, now I have to use this equation here. So I have to calculate the AGV, okay? So the AGV basically ends up being the, I don't have the AGV written anywhere. Oh, I'm sorry, I thought, okay, so the AGV, okay, is basically this length here from there to there. That's the amount of steel that's going to shear times the thickness. And that's what I have here. I apologize for not writing it separately, but this is what this is. This is AGV here. It's this length here. That's the that's the length that's going to shear off times the thickness. And that's my AGV, okay? Now, I put everything in the equation. Now, guys, I've seen this classic mistake every time. People calculate this the first time, they multiply by 75, and then they add this part to it. Work everything inside the brackets, and then you multiply by 75, okay? I've seen that classic mistake year after year. So therefore, I put everything in terms of T. I solve for T, and wow. I need a plate thickness of 9.51 millimeters. So far, it looks like this is where it's going to maybe fail. Okay. Now, the last place I got to check, of course, is 5.5, where I have an AGV here, an AGV here, and all I have here is the S squared. I have that area of S squared, okay, the G over T. So therefore, I have WNT S squared over TE. Okay, so I have 140 minus 30 minus 30, which gives me this here, minus 26. I'm going through one bolt hole, half here and half there. So that gives me the WN. And again, then this part here gives me the diagonal, additional diagonal value here. So I end up, that's my A and E. That's where this is going to fail in tension. And then this part here and this part here is going to fail in shear. So therefore, now you see here I have 60 plus 30. Okay, it's 120. I should have shown you how to get the AGE. Basically, I apologize for that, because here I have, from here to here, I have 60 plus 30, and then I have another 30, so that gives me 120, and that's where I get the AGV value. Okay, and then that's in terms of T. This is the average between the yield strength and the tensile strength. That's what you take. And when I do this calculation properly, I end up getting